So today we are going to talk about Observability Data Lake, its motivation and methodology. So before we start, I want to introduce ourselves. We are from Greptime. Greptime is making a database for or data lake for observability specifically. And my name is Ning, and I'm the CTO and the co-founder from Greptime. Joining me is our database engineer, Ruihang. He's also the PMC member of Data Fusion project, which is the open source query engine. I think Data Fusion is the most exciting open source project in the last few years. So you can reach out with us from the email, and we are also very active on GitHub. You can find us. So observability is the new big data. Observability is the big data for DevOps. We have been extracting all types of information from using observability tools from the application state, the resource consumption, and maybe even cost and minimal. It has been the most important input for our DevOps loops. So the observability ecosystem, the landscape is very complete, very complicated, very crowded. So there are a lot of services, protocols, formats, database, vendors you might heard of. So I created this V model to demonstrate the data flow in observability, and I also help you to understand the architecture better. So the left wing of this V model is how data ingested in observability. So from the right up corner is the agent, some language SDKs. So once the data is collected, it's encoded in some standard formats, so go all the way down to the database. The right wing of this V letter is the data application path. Typically, it's a dashboard or some alerts notification system. It uses some standard query language or APIs to retrieve the data from the database. So we can divide this V model into 3 layers. So up the top layer, I call it a semantic layer. So only at this layer, we know the meaning of the data. For example, you have a matrix called HTTP request count. Obviously, it's a counter for your for the application request your application has processed. So on the other side, we can put up together a dashboard, including some visualization panels. We call it HTTP stats. So at this layer, we know the meaning of the data. If you are familiar with the Datadog's onboarding process, you know that they ask you to install their agent to your server. So once the agent is up and running, you will be redirected to a dashboard with data visualized. So this is where Datadog works at. The semantic layer is their interface. Second, the data access layer. So when people talking to you that they are using OpenTelemetry for observability, they are actually talk about this layer. So the next layer is the storage layer. So when people talk to you that they are using Greptime for observability, they are actually talking about this layer. So in observability, there are historically, due to historical reason, there are 3 types of data: the metrics, the logs, and the traces. Each of type has their own data pipeline go through this V model. They have their own protocols. They have their own database and their own applications. So today we are talking about observability in the big data area. So from big data perspective, this is obviously a problem. You can say that the data is divided into 3 independent data silos. So all the data is created, transported, stored, and queried independently. This is going to create some problems. First, at the data source, it might introduce some inconsistency of metadata or even data itself. For storage, it's introduced redundancy of storage. And for the application layer, due to the different data granularity, it's very hard to combine them together. Actually, I think at the moment, people are using their own brain to join all this data together. There is no such major application that can join trace, metrics, logs at the moment. This is the issue one, the data silo issue. The second is the data, especially the metrics, is pre-aggregated. So this means we lost the original data. We can only use the data that originally aggregated from the data source to display in the dashboard. If you use digital camera, you know that there are typically two types of output format. One is called a RAW format, and another is JPEG. JPEG is often faster and smaller, but RAW format is give you more post-processing options. So this is the same. The issue three that you can only do what you know. You can only collect the data based on your experience. That because metrics, logs are all explicitly collected from the application. So you typically do it based on your own experience, your team experience, or the best practice from the community. For example, Google SRE cookbook has the 4 golden metrics. Yeah, but you always hit this unknown. So once you hit this unknown, you have to go back to the development phase to do code change and go through the release process. It may take maybe hours or days or even months to get the code online, and you can retrieve the new data. So I think this is the 3 major problems of current practice of observability. And let's check how data lake approach can help. So obviously, the first step is to replace the database with a data lake approach. Yeah, a data lake approach is typically using something like object storage to reduce the cost. Also, it's more scalable. But this is just the first step. This is not everything for observability data lake. So next, we want to resolve this data silo issue. So to resolve this, we want to remove the 3 pillars of observability with a new concept called wide event. Wide events is it's like logs, but it's from a different purpose. It's context-oriented JSON documents. It collects as much context as possible for future analysis. For example, if you are collecting these wide events from HTTP handler, you automatically get maybe request context, the session context, the user information, and maybe even database context. You have a database connection. So all these contexts go to a single data storage. This will be your single source of truth as storage. You will still have 3 pillars, metrics, logs, views, but they are not the data itself. They become the views of data. So this is an example of wide events. It might not be clear, but I don't want, you don't need to read it's clear. You just need to know that it's a JSON document with a strict structure, and it contains context information. It's not designed for a particular problem. It's for a general purpose data collection. Second, pre-aggregated issue is also addressed because we no longer do aggregation at the data source. All the aggregation will happen in the data lake. It can either be the query engine. We can use SQL to aggregate data. We can also use the materialized views, the in database flow engine. streaming engine to do some speed up. So this will add more capabilities, more possibilities for AI application and also actionable observability tools, because we have the raw data. We can provide more information to these AI tools. The AI tools is very good at making decisions based on the context information. And this is to address the pre-aggregation issue. And the last one, you no longer have the static instrument, because the data you collect is based on the fact, not based on a particular problem. So the feedback loop goes to the data analyze under the database. You no longer need to go through the development loop to get the result. You just send the exploratory data analysis query to the database. It may take minutes or even seconds to get the result to validate your choice. So to wrap it up, observability data lake is about first using a data lake infrastructure to organize the data, to store the data. Uh, the infrastructure should have a capability to handle a large amount of data, because we are now storing raw data instead of aggregated data. Also, it has the capability to deal with different query. It should be very flexible for short-term query, real-time query, and maybe long-time analytical query. This is the first thing. The second, it should have affordable data storage. It's typically based on the object storage, because it's I heard it's only 10% cost if you compare to local disk. We are storing as much raw data as possible for our feedback loop. So this is very important. And the architecture has to be elastic and scalable, so we can do analytical query. Yeah, it may take a lot of resource to do that. So the database has the capability for that. So this is what we are doing at Greptime. We are working hard to deliver such a data lake infrastructure. And the second, the data lake practice encourage you to collect context-rich raw data as the input for the data source. The three pillars still exist, but it's no longer the data itself. It's the view, it's the visualization, and we all got faster feedback loop for exploratory data analysis based on the for this unknown fact. You no longer need to define your problem and validate through an online release process. At last, everybody is talking AI these days. So the raw data, the context-rich data is a great data input for the AI, for the possibility to give AI more application to integrate with observability. Okay, so that's enough at the concept level. I will invite our engineer Ruihang to continue for the practice level.
Okay, thank you, Ning, and good morning. Hello, everyone. And next, I will introduce from the practice level about we choose three things we think is important for doing observabilities in big data level. So the three choice things the first is about JSON. Like mentioned before, how we use JSON to express our wild event data and how we make it more optimal and make it high performance. And the second is about SQL, SQL and more. A query language is an interface you interact with your data. like as a human or as an AI agent. And we will introduce how we implement it and what we provide in Greptime DB to like make you interactive with your data. And third about is index. All of these are very old techniques in database or data lake, but we will introduce why index is important for us and why index is important for observability in data lake. Okay, first, Jason, like from a selfish infra engineer's perspective, I think it is not a good choice for data operations. We often wish our user to consider a perfect and fixed schema for their data, and they should choose their index or design their queries wisely and truthfully. And we don't expect to receive some question like, why deletion increase my data size? But we know that is impossible. So we, as an engineer, we should accommodate to our users. And so the reality is JSON is widely used. I won't say it's good enough, but it's a de facto for maybe data and for like LLMs. So we should make it better. So here in the observabilities in data lake, we use JSON as data format to express our wild event. Everybody knows by making optimizations is to make limitations. So to make wild event in JSON best suit for our use case and our system, here is some limitations and pre-requirement we made. We previously categorized all JSON scenarios into 3 cases. This is unlike some more general JSON use case in data lakes or big data. And this is also not like how a traditional monitoring system like Victoria Metrics or Victoria Logs or Grafana Loki handle JSON things. We do them in observability with data lake ways. And the first still takes the example from Ning. The first thing is, and the most common case is, for most of the time, we know the data, we know how our data looks like, and we know how will us use them. And for some fields, we even can figure out or give them a concrete data type. Like for all trace event come from a HTTP handler, we know the must contains a method and maybe a status code. They may be vacant, but if then present, it will be this. So this is the first. We can treat them as a fixed schema and the most common case. And we can even build some, we can predefine some necessary index for them to accelerate our queries. And the second, sometimes there will be some evolution of schema. We may want to add or remove fields with time passing by, or we may want to change some data types for a field. For example, here, like timestamp, we have 3 groups of timestamp. They are duplicate, and we may want to remove some of them. And timestamp here are represented in a human readable string, and maybe for days, for some reason, we want to change it to a Unix timestamp, which is numbers. So here we introduce variant of schema and the data types. We can change it as later because the JSON itself is not schemaful. And the real thing is you may just accept and output something from your user and you don't know what it is and you also don't know how to use it or how it would be used. So to resolve all of these and bring you a promised performance and cost, the cost of your entire data and your system over that dynamic data of JSON. We have made some optimizations. And the first, and I think the most important things, but it is not new, is to convert JSON into a columnar format. Each JSON is a row of records, but to like optimize your query performance or reduce your storage costs, we can put them together, put the same fields together. The more same things we put together, we can naturally improve our compression ratios, and we can do some vectorized computation by like doing one operation in one field of all records. And here I take the screenshot from JSON bench, which is made by ClickHouse. And this graph shows our data size after ingesting 1 billion of rows of JSON data. The example JSON data is taken from Blue Sky. And we are the second small things system in the entire board without extra compressions. And due to the space limit, I haven't put the query result, but we are also the top one or top two system in the query aspect. So, and you can easily figure out if we store things in columnar format, it will end up with a schema for implementation, and that's true. In the entire system, considering your infrastructure and your business system together, the complexity won't disappear for some reason. It only in transit. So we translate the complex to the infra set, to our set, to make user can use it easily and helpfully. So here we like to achieve this, we use two not new technique, two old things. The first is to auto change your schema, to auto create columns or new fields for JSON incomes to the system. And the second is to use dynamic mapped types. So you may ask if you want to do these extra things instead of store JSON as a raw string as it comes, it must introduce some computation and overhead. So when do you need to pay for this? We designed based on our previous three assumptions to achieve, we think, the best for the entire system to reduce the global cost to a low level. So actually, simple speaking, we have two paths of we can take actions. The first is when data comes, the write process. And the second is when data out, the read process or the query process. For the first, the most common case where almost all schema are fixed, we choose to do them in write. And we will decompose all incoming JSON data and map the like some parsing from string to numbers and to build index in the write. And if we do this for the most common case, we only need to pay it at once, pay the overhead at once when data is come. And for all following read, you don't need to do anything with like zero cost. And for the second case, where we have dynamic structure or dynamic data types, and forget to mention, the Greptime DB is built like, generally speaking, is a LSM tree-like structure. All of the data are organized in blocks, where each blocks can have different schema or different data types. So for the second thing, for both dynamics, we handle it on the read, but we will like cast something cast into a common tab when generating a data block files. And when we encounter two data blocks with different like schema or tabs, we will do the runtime cast. As this is come with a relatively low cost, because if you don't do this, you will still encounter some like for a traditional database, you can alter a table, or for computations, you will need to cast your data types to fit the operators, to fit the functions. So the second, we choose to pay both on the write and read. And for the third thing, the third aspect, where the data are mostly dynamic and harder to use, we choose to like store them in a plain JSON string and to parse them runtime to reduce the cost of write. So by doing this, you pay the most cost on write for those data you will use frequently, and you pay no cost for those data you are hardly to use. And yes, this is our approach on making JSON things. And the second is about query language. You know, considering the audience today, and I'm not going to emphasize how important the SQL plays in the database systems, but occasionally I count the systems yesterday, and I found around half of the systems are not directly associated with SQL. So I think it's still worth something to say it out. Like the SQL is the most fundamental language for our modern data infra. So literally you can do anything with SQL, but the reality is you won't do anything for it. You don't like you don't wish to write 100 or 1,000 of lines to just render a dashboard to see a few lines. This is not practical. And in observability, the good thing is you actually don't need to express anything with your query language. You like the things you will need to do with your wild-event data, with your observability data is kind of limited. For example, what you want to do is only draw lines for some sensors or some metrics in the past few days, or like grab some latest 100 logs of your some components, or to extract traces and or its relevant spans from trace ID provided by your user, or from something you want to do inside. So it is not harmful to introduce some DSLs. I know many DSLs are not good for an engineer, and it will increase the load of your learning. But as our practice in observability scenario, some DSLs do help to save your lives. For example, the maybe most well used DSL PromQL by Prometheus. Many of you might be having use of them. Uh, it can draw lines in a very efficient ways. It can maybe replace 10 of SQL with one line of PromQL. Yes, but as we are going to combine all three products together and make them to become a view, we like can't choose, or there doesn't have a one thing for all. So what our choice is to make everything run can be possible be run in Greptime DB. And here is our architecture. If you're familiar with the programming language, how a programming language is implemented, nowadays they are separately well into two parts: the front end and the back end. Where back end is mostly the LLVM, and the front end is what that compiles things into LLVM. And here is how we deal with our SQL or PromQL or any other DSLs you can name. Uh, First, we implement our backend, the execution engine based on data fusion, and we take the traditional database things where the plan are implemented in logic plan and logic plan optimizer, and then convert to physical plan or execution plan and then optimizer, and then execute on the execution plan. So by doing this, all you need to do to add a new language to GreptimeDB is to first write a parser and then convert the parser into logic plans. Easy 2 steps, you can get a new languages in GreptimeDB. And the there is another cool thing is by doing this, it is not common in programming languages, but you can do this in GreptimeDB, that you can write different languages together in one query, and let each of part to handle their best aspect. Like, for example, in current of GreptimeDB, you can first write a prompt queue to analyze all of your metrics data to get a time series, and then do some post analyze with SQL in one query. Because as the architecture shows, when they come to logic plan, there are no difference. They are not distinguishable. So by doing this, we hope to provide a union way and union interface that can handle almost, maybe not now, but we keep the possibility to handle all observability scenarios in one system. And the third is about indexes. So I work with observability data every day, but I have to say, yes, we call them junk data. Unlike your business commercial data, which where every single rows of records of your data is referred to a transaction or maybe a bank transaction. But this is not how observability data looks like. You can't tell anything from one single number or one single trace span or one single log. Usually you have to combine many of them to tell one story. So it becomes very verbose, but each record have a limited value. Our storage costs and our compute resources will become much expensive, even compared with our commercial data. So this is how we do to resolve this. We trying to make the index. It's still the work in the traditional database system, the index, but it plays a kind of different roles in observabilities in data lake. For index here, we are not or we don't need some complex things like Postgres provided, but we will need to provide all index based or related to our use scenarios. And we are kind of, in our practice, we use index to define our workflow and our workload. For example, at least the three most common use index in GreptimeDB, the inverted index and skipping index and full text index. From the name, you can figure out they are faced for different data and different user scenarios. The inverted index, which is highly accurate, but it comes with a high cost when the time series or the combination of your labels goes high. In the other side, the skipping index is pretty small and also keeps a good performance, but it is very sensitive to the ordering of your data. Like you have to give your data good ordering that can release the power of skipping index. Whereas the full text index, you can search almost anything on top of it, but it is much more robust compared with even inverted index. So after you ingest your data into GreptimeDB, you will need to define how you will use it. Like this also looks like you define your views and you get your logs, your traces from your wild event data. So in our practice, we like for a scenario where the logs, we want to do some full text search, and at the same time, we want to extract some timeline or time series from the same of data, we can, for example, put skipping index and full index for it. So by doing this, we can get a good performance of either a single point gate and as well as a full text search. Okay, this is how I choose the three important things in the GreptimeDB to face the big data in observability challenge. So there are three parts: the JSON as a data model, and the unified execution engine with SQL and more DSLs as a query interface, and the index as we think is the next step and concrete step for handling large amount of data with limited resources and limited budget. And okay, that's all. Thank you.
All right, we have some time for questions. Would anybody like to ask Ning or Ruihang questions? Oh, wait, just wait 1 second. Costa's gonna bring you a mic.
Okay, you talk about how you use the JSON and the query language is DSS or SQL. So we talk about JSON. We also use maybe MongoDB is better than PostgreSQL or some others. So why don't you use MongoDB to handle the JSON part?
Yeah, great question. First, MongoDB comes with some limitation. I categorize it into the first things mentioned, like the traditional data lake ways of handling dynamic data. Because for MongoDB, I remember the first limitation is when your JSON or your event come with a list. For example, this is very common in trace scenarios where your root trace span may follow with many of sub-trace spans. But in MongoDB, you will need to define, like repeat every root trace span with a sub-trace span, and it just doesn't like a tree structure of your data. And the second is, for example, if you want to in a while event, where in that example we have a latency of the HTTP request, and if you want to draw a line, like using PromQL to draw a line on top of that data, you simply can't do this in MongoDB because all you have is JSON and a document, and it is not aware of some concept of time series or other things you want to do with traditional time series data, or you want to draw a dashboard on top of it. Simply speaking, it's not specific for observabilities. You may can do something on top of it, but that might not be the optimal ways. Thank you.
Oh, I noticed this is the columnar format database, right? So it was developed on top of the Postgres database, or else it has its own the scratch level development process. Because when I noticed there are three indexing formats you mentioned during your presentation. So when it is a columnar databases, how you are going to build up the indexes and the storage format, whether it is a cloud based or also on premise. Because I entered a little late, but that's the reason I'm asking, because when it is storing your data and retrieving for the indexing in the columnar database, in the JSON file format, you are storing the data. So how it is going to be build up the indexes and pull and push the method from this database, how you are going to can you explain it? Then it will be useful. Yeah.
Thank you. The question is how to like build an index on top of JSON data, right? Okay. we transit the complexity from user side to our side. So what users see is stores JSON in the Greptime DB, but internal of Greptime DB, we are treat them as a plain column things. This is also another old techniques we are using for. We use Parquet and as our underlying storage format. Well, if you are familiar with Parquet, Apache Parquet format, you can figure out it is a structural format. It can handle any types of nested structures and any types of list or structure or dynamic maps and something. So we do this in two steps. We first convert all necessary JSON part into a column. So in the after the storage level, all you see is a column of data, not JSON. You don't see JSON. JSON is represented as a semantic label on top of the storage engine. And all storage engine need to handle is to build an index on this column of data. So it is just like how other things was done. Like if you want to build, for example, a min-max, you simply scan the column and you get the min-max. And you can use it as a zoom map.
And also for the first question you asked, if the database is based on Postgres, it's not. We build the database from scratch. We build the storage engine by ourselves, and the query engine is based on the open source project Data Fusion. And I think we are the largest code base of Data Fusion project that you can say it as a Data Fusion distribution, a real world Data Fusion application. Yeah.
One question on the data fusion part. So you mentioned like you rewrite the front ends into logical plan, physical plan, and then the execution happen in data fusion, right? How do you handle like adding external indexes for like posting lists, keywords indexes, lexical indexes within data fusion? Is that like a joint query that you run on the fly?
Your question is how we like use dynamic things in data fusion?
Index.
Yeah, how do you handle external indexes? Because data is Parquet. You run that into data fusion. So
that's a good question. And yeah, I haven't mentioned the right part of this architecture. And as you can see, if you are familiar with data fusion, or this is similar with any other database execution engine, and what we use from data fusion are the middle part, the for part. And after a physical plan is going to be executed, we first focus the data source part. We only use data fusion as an execution engine, so the interface is we feed data into data fusion, and the index is applied at this step. So we use index to filter out efficiently what data should be fed into data fusion, and data fusion only need to do some other computations like aggregation or join.
right, so it's like implementing in the table source, and you feed a stream of batches from.
Yes.
Okay.
Yes. And some of the physical plan, we have rewrote them, rewrote our own version to replace the data fusion version. So make them to be well aware of some high-level business semantic like time series things, or the low-level storage things like, for example, we implemented a more efficient sort on top of data fusion and replace the data fusion sort, because when data is ingested into Greptime DB, we will do a sort for them, like to sort them on the timestamp index. So if later user want to query something also ordered by the timestamp, we can convert the full maybe quick sort into a merge sort, which can reduce the computation by a lot.
Yep. Thank you.
Thank you.
All right, one more round of applause for the Greptime team. If you have any other questions,